Welcome everyone. Thank you for joining us at this meeting. I'm Adrian Buryło, product leader at Servo and Motion Group in Mitsubishi Electric. Together with me is, as always, Boże Siudaj, product manager. Okay, good morning. Product manager at the same product group. I wanted to add it. So today we will be speaking about speeding up the servo applications, making the performance of this application bigger. We hope that you can see us, that you can hear us.
Please confirm on the chat.
Please confirm. Oh, there is no. Okay.
Yes, okay. Thank you.
Thank you very much. Before we start, few organizational things. First one about what is on the top. So on the top you can see this bar, this blue bar with green button with the name "How to speed up your machine." And if during our presentation you will think that, oh, it's nice to hear that, I would like to discuss it more, then please just click this check button, and then we will be able to contact you and make some kinds of the consultation discussion on your own machine. So it is possible. Of course, you can click now, you can click later. I will also remind it on the end of the webinar. The second thing, of course, you are welcome to ask us questions, but please write it on the chat with the question mark, because in this Click Meeting platform, when there is a question mark on the end of the sentence, we'll be able to easier find this question and distinguish it from normal chat conversation. And did I forget about something?
No.
Or not? Yeah. Of course, we'll answer all of the questions at the end of the webinar. So after our presentation, we'll look on the questions and then we will answer it. So you are welcome to ask these questions. Please ask the questions, because I think it is better, yes, because the discussion then is better and you can learn some more from us, and also we can learn from you. Okay, so I will share my screen. It should be already visible. I will just, okay, here. So it's visible. And I think we can start. So the question is how to speed up an application with servo drives.
Title, interesting and catchy, I would say. But in general, why are we even talking about this? Well, because now everyone these days wants to produce more, faster, better, and of course, cheaper.
This is the everyday walking life in the sales. It has to be fast, good, and above all, of course, cheap. So in a word, a classic.
Yes, but it's not without a reason. Currently, you can see the market flooding with machines from different, let's say, cheaper parts of the world. For example, from China, which are taking business away from us locally. So what can we do to defend our local designs?
For example, also compete on the price.
How it's possible, Adrian?
We have to measure this price a little differently, considering the ROE of an application, an indicator that shows the profitability of an investment over time. In a nutshell, calculating it for a purchase application comes down to subtracting its purchase and implementation cost from profits that this implementation will bring us at the plant.
The question is how to increase the ROI for the end customer.
Increase the net profit of the machine, for example, increasing its efficiency.
Yes, that's it. Speed up your application.
Exactly. Then how can you do it?
Let's start with the head.
From the head?
Yes, from the head, from the control system.
Okay, then how, let's begin from the start. Yes, then how are the servo axes controlled?
In modern machines, we can divide the control into two types, point-to-point and motion, while both have their advantages and disadvantages. Let's take a closer look at them from the point of view of machine acceleration. Point-to-point control works on the principle of sending a movement command and waiting for a signal indicating that position has been completed. all control of the motion loop is done on the amplifier side, although we have feedback from the drive about the current position, status, etc. This is subject to an error due to the timing of the communication cycle. In other words, it is information at the time of sending, not the actual current status of the drive at the moment. This uncertainty can cause problems. Therefore, when you have several drives, you need to be sure that each one is in the right position and you don't have to wait until the one has finished the moving before the next one can move. In short, the drives must not pass each other because this can lead a collision. Second, motion control, on the other hand, is where the motion controller monitor position loops and send each drive a new target. So you can work multiple drives in collision space and pass each other without wasting time until one or other drive move away. This is possible because it's the motion controller that calculates the trajectory of the drive's movements, and we can build more complex passes without overloading of the amplifier.
Motion allows you to use functions such as the cam, which works on the principle of a mechanical cam, of course. In a cam case, its special shape results in a specific movement profile, for example, linear. Such solutions are used, for example, in the valve train of internal combustion engines, where cams control the operation of the valves. The electronic cam works on identical principle, only the cam parameters are set directly in the servo program. In this way, we can control, for example, the position of the drive or its speed over time. A good example of an application where such cams are used is a servo filling. Due to the varying cross-section of the bottle volume, as you can see on this picture, using the same nozzle pull-out speed would result in overflow or foaming of the liquid being filled. To prevent this from happening, a cam is used that varies the speed of the nozzle drive depending on its position relative to the bottle. But such a flagship application of motion is, of course, synchronization. It is impossible to do in the point-to-point control. In synchronization, the motion controller sends targets to several servo axes at the same time. This allows us to synchronize their movements so that, for example, the first drive follows the second drive with a specifically set offset or simply copies its movement, so that both axes move simultaneously. This solution is used, for example, in a tandem axis. Typically, a mechanical solution is used in this case. We connect both linear axes via long shaft, but this is not always the optimum solution, especially for a large moving masses. We lose precision and risk skewing the drive element. In addition, this significantly increases the moment of inertia reduced on the motor shaft. And synchronization motion allows us to use two drives, each for one linear module. We gain in accuracy, in the power, because by dividing the mass into two drives and not having components that increase inertia, such as shaft, we are able to fit smaller capacity drives and have less torque loss. Plus, it is a much more compact solution. We also get rid of mechanical components that have a low service life. So for tandem system, the two-axis servo amplifiers we have in the portfolio are ideal, as we can also save the cabinet space. In real-life applications, like the one showed on the video you can see, synchronization is most often used to connect some two elements of the machine cycle that work closely together. Here, an example of a print application from our partner Keller. A very visible synchronization of the linear axis performing screen printing on a bottle supplied by a rotary axis. And another variation of synchronization, often distinguished in motion controllers because of its ready-to-use parametrization functions, is interpolation. With it, we can combine the movements of two or more axes such that they make interpolated linear movements, as in the case of the square and triangle in the application shown, or circular in the case of the circle. Because of these uncertainties in the point-to-point control previously mentioned by Błażej, if we try to program an interpolation, for example, circular, at best it would come out with an ellipse. But I also talk a lot about that. But just wait, Błażej, because motion is rather associated with expensive technology.
Yes and no, because we can use cost-effective, compact controllers that support motion functions.
Okay, so you mean the IQF series controller, because you are probably thinking of them, and they are kind of small giants. They allow up to 24 servo axes per one PLC. So they are ideal for small and medium-sized machines. It is only above this number, so above 24 axes, that we need to equip application with a strongman, so motion on IQR series controller. So we can actually speed up the machine and not go bankrupt trying.
A suitable motion controller is one thing. The question is also on which network it is connected.
Well, for example, via our own CC-Link IATSN network, which allows point-to-point and motion to be controlled within the same network, increasing flexibility of the choice. Look at the network configuration. In the case of the 4-axis motion module, which means that we can control up to 4 axes in a full synchronization, you can still add between 116 and even 348 such servo drives in the configuration. This is ideal for example, positioning axes that do not need to be synchronized. In short, you speed up your application by optimizing the application cycle time for synchronized access, and in addition, by exchanging data in one network with the other devices without worrying about delays.
Another extremely important thing is safe stops.
So, STO?
Not quite.
What do you mean? Isn't it just about making the machine safe?
Yes, it is an important aspect, but what also matters is how long the machine is restored to operation after being put into a safe state. We say this because after typical STO or even SS1, it takes a while for the drives to resume operation. By using advanced safety functions that don't remove voltage from the amplifier end stage, it's possible to reduce downtime and start immediately just after safety system has been set up.
What you are talking about is very important in terms of application performance, and I happen to have a great example illustrating this mechanism. So by using two-zone light curtains, for example, we are able to bring the drives to an efficient safe stop in the event of operator interaction. When approaching an application, we will first use the safely limited speed function, which will limit the speed of the drives, reducing the chance of injury. And once a specific distance is exceeded, the drives will stop via safe operation stop. Crucially, once the operator has left, we do not have to rearm the machine because voltage is applied to the drives all the time. So they will start automatically without any unnecessary downtimes. I showed this on the pick and place application with the robot, but safety function of this type can also be used on our latest MR-J5 servo drive series. Whether you want to use simpler functions such as STO or SIS1, or more advanced ones such as the SLS and SOS shown, you can do it with the same amplifier hardware without additional licenses. What is more, the MR-J5 supports this function not only over the cable, but also over the network, both our own previously mentioned CC-Link IATSN and also EtherCAT, so with fail-safe over EtherCAT.
Another important topic affecting productivity will be the control algorithms inside of the servo drive, resulting in the effectiveness of auto-tuning. In the animation, you can see the difference between a well-functioning regulator and one that is not performing well. A very efficient regulator loop and auto-tuning algorithms can significantly improve the cycle times as the servo will arrive at the exact point without any overshoot or even oscillation in the end position. In addition, the performance characteristics of the servo drive will be better overall, resulting in a smoother and more efficient movement. Getting the right controller parameters through manual auto-tuning would be in many cases impossible. We would have to settle for a less efficient application.
Yes, the quality of the control also further increase how much load we can maximally connect to the drive, which is why we pride ourselves on the high recommended moments of the load to motor inertia ratio.
I think we have already covered the issue of control and how it affects to the performance of the application. Let's now deal with the drivetrain.
So we will finally start to increase the speed of the motors.
Not really. Acceleration is more important in the context of servo applications, which are mostly start-stop. If the maximum torque of the motor doesn't allow achieve higher acceleration value, we can use the torque increase function. This function allows you to take advantage of the higher current overload capacity of the motor, and when connected to the higher power amplifier, the maximum torque of the motor is significantly increased in the lower speed range. For comparison, the characteristic curve on the left side is the normal curve of the motor, and on the right side you can see with the torque increase, where you can see what I mentioned.
So to illustrate this better, let's look at the example of laser plotter application. The maximum acceleration we can achieve on standard 1.5 kilowatt motor connection is 72 milliseconds. By using a larger amplifier and this torque increase function, we are able to reduce acceleration ramps to as low as 55 milliseconds, a value that would be not possible without this additional 100% of torque. By default, in such a case, you would have to use as much as 3.5 kilowatt of motor power. So this difference is really noticeable, and especially in applications requiring high acceleration, such as plotters, we'll be able to make proper use of this function. After all, we want to accelerate applications, don't we? I think at this point it is worth mentioning the motor overload characteristic, which I also talked about a few months ago in our first webinar on drive sizing. The overload characteristics is not very often shown in manufacturers' catalogs, and wrongly so, because it shows how long you can overload a servo motor with different torque values in relation to the nominal torque and time. This is important information when considering accelerating applications, because getting higher torque is one thing, but it is also important how long the torque can be generated. Of course, the motor's mean square torque must be in the nominal range, but the instantaneous overload torque can be applied to the motor according to this characteristic, which can be found in our documentation.
All right, but what if we can't use the overload capacity or the torque increase because the mean square torque is above of the nominal value?
Then you can use the size of the motors.
The size of motors?
Yes, because usually accelerating a machine will involve increasing the power of the motors, assuming the originally installed ones are not oversized. Only if we don't want to fundamentally change the design of our application, or you want to do such a replacement on an existing one, then we face a problem: space. Because a more powerful motor is always a bigger motor. With that said, our motors are very small and may well be this can be an answer to this problem. The size of the motor in our previous NRJ4 series of the drives, typically from the low inertia class, the 100 watts KR motor, is a 40 millimeter flange and 82.4 millimeter long. In the MRJ5 series, using a 50% more powerful motor with the same mounting dimensions, we have a length of 80.5 millimeter, which is less. The same is true for 400 watts and 600 watts in the MRJ5. Same connection dimensions, and the difference in length is only 5 millimeter to the disadvantage of the motor. This is the one that is more powerful. Another example where we have an extra 50% power in the same dimensions, and there are more examples like this in our portfolio. This is particularly significant when you consider that the MRJ5 series that we compare the MRJ5 series to is even now regarded as very compact solution in the global servo market.
Once we know that we can increase the overload torque of the motors, and we can also reach for a larger motor without dimensions change, it is worth nothing another thing: power rate.
So you mean the capacity of the motor?
Not really. I mean the ratio of nominal torque squared against the inertia of the motor.
Okay, so what does it affect?
It is the value that shows how much electrical energy in kilowatt we can transmit from the motor to the effector per second.
Okay, so it defines how fast we can accelerate.
Exactly, but here we have additional classes of inertia of the motors.
Yes, because we have a class of medium, low, and ultra low inertia. This inertia relative to nominal torque defines for us how rapidly the motor can accelerate.
Okay, can we illustrate it somehow?
Of course, this time I will use every man's favorite toy, cars, as an analogy, so it will be easy to understand. So firstly, let's start with the medium inertia motors. They are like the trucks. So what is about the truck? It can drive a very big load, yes, a very big load, but trucks are not most dynamic cars that you can find on the road, yes. So I don't think that you will be see the truck that is trying to overpass somebody on the lights, yes. But this is the case for these motors. They are not the most dynamic. They're still dynamic because, of course, they are the servo motors, yes, but they can drive a very big load. So they are typically used, for example, in the lifting applications, yes. The low inertia motors are like the standard cars, standard family car. So it's possible to drive pretty big load, yes. So you can go on the holidays with your children, with your wife, a lot of luggage, yes, and still the trip will be pretty comfortable. From the other side, with, for example, a smaller load, you can still be pretty dynamic on the road, of course, depending on the power of the motor, yes. But this is the same of the power of the motor of the car. But this is the same for the low inertia motors. They are like the equilibrium, yes. So they are the point of the most standard motors on the market. You will mostly see low inertia motors in a lot of applications because you can use them to drive a load with pretty big dynamic, and the load can be also pretty big, yes. So in most applications, like, I don't know, pick and place and so on, I think you will see this kind of motors. And lastly, ultra low inertia motors are like the supercars, yeah, like Formula One. So the dynamic is on the biggest possible level. They are very dynamic. They can accelerate very, very quickly. But from the other side, it is not always possible to drive a very big load.
Well, on this occasion, it is worth mentioning whether it is worth adding gears or not.
In my opinion, it is almost always worth it.
Let's make an example. Looking at the example of 200 watt motor with 4-to-1 gearing and a 500 watt motor without gearing, from the point of view of the nominal torque, it will come out similar. Maximum torque will be lower for middle inertia motor, but for the most important is usually inertia. From inertia point of view, these two sets will be able to cope with a similar load. How to calculate this? We have motor inertia multiplied by factor from our catalog and optionally multiplied by gearbox ratio squared. As you can see, the max inertia for both motors came out to be more or less similar, so both could fit to the application. But now let's set a working point for the speed at the output of the gearbox, for example, 1500 RPM. A motor with 4-to-1 gearbox will need to accelerate to 6,000 rpm, while a motor without a gearbox will still have a significant speed range free. You can see this through the red lines in the graph. So even though in theory 500 watt motor middle inertia motor is slower, in real application at similar cost it will give us the possibility of increasing the maximum speed, and it will remove a gearbox which also puts up some resistance and wears out. It's possible, provided of course that we will be able to fit a motor with a much larger flange to the angular acceleration of the middle inertia motors will be sufficient to meet our requirements.
Okay, sorry, but slow down, Patrick, because I think both me and the viewers are already steaming slightly. Angular accelerations?
Yes, because when building application with very high acceleration, it is worth remembering that the motor rotor is a load for the motor itself. Therefore, for mega dynamic applications, empty RT motors with ultra low inertia should be very useful, especially in gearbox systems, where in order to achieve the set speed at the output of the gearbox over time, angular acceleration reach high values and torque losses to the motor inertia are strongly visible.
I think now I know what you mean, but let's show it with a real life example.
Well, then let's take an application I sized last week's, a rotary knife application with 6 blades. For the same configuration, as can be seen in the table in the central, the middle of the slide, ultra low inertia motors, so HKRT motor, have about 30% lower effective load than low inertia HKKT motor. The cutting cycle lasted 0.1 second and can be seen in the figure of the right. This is because at high dynamics, we don't have to lose much driving torque to accelerate the motor itself.
Okay, and what were the parameters of this motor?
Okay, so on the left hand side, you can see 2 kilowatt low inertia motor, and on the right, an ultra low with the same power capacity. The ultra low inertia motor has about 4.4 times smaller inertia, and it is very noticeable in that case. Again, let's show the table from the sizing software. As you can see, the low inertia motor with the destination KT is on the limit, and the ultra low RT has a very safe reserve of torque.
So in summary, let's look on the graph of power rates values for ultra low and low inertia motors as a function of their power. We can see that the rate is clearly higher for the lower inertia motors, so ultra low inertia motors, so RT and MT motors, gray and yellow line. And that it increased dramatically with power. 2 kilowatts RT motors have more than 4 times the acceleration capability in comparison to KT. And at this point, I think it is worth mentioning that a motor running with such a cycle will have an additional super function, the hull heater. So therefore, as we have said several times in our previous webinars, if you want to check whether the motor you are currently using is properly sized, it is worth checking its temperature. It will be rather warm, or it should be rather warm. So as we are already slowly approaching the end of this webinar, another thing we can accelerate considerably are actuators driven by the other media.
You mean hydraulics or pneumatics?
Yes, they both work similarly, but it's pneumatics that are most often used in faster application. So let's just focus on it. Then what control do we have over the acceleration of pneumatic actuators?
Okay, in pneumatic actuators, traveling time depends on pressure and flow. Over time, due to the leaks that develop, we will have to use more medium, which is very negative for the energy efficiency, but that topic is for totally another meeting. Let's go back to accelerating the machines, because all in all, at certain point we will reach the maximum pressure point and flow. And there will be no way to accelerate the actuator. Moreover, the machine culture will be bad, the actuators will wear out quickly, and we can't take advantage of the other control benefits that the servo system gives us. Because in pneumatics control, you can find different options, but most of the time, however, in most applications, we have actuators with end position sensors, and we don't know what is happening between them.
So it's like point-to-point control in a servo.
Yes, yes, yes. Only we don't have continuous feedback on the position. So from sensor to sensor, we are blind. Besides, when there are pressure drops on the machine or in the network, we can't achieve the target cycle time.
Okay, but then how could you accelerate a machine equipped with such a system?
Replacing pneumatics with electrical drives. For longer movements, it's the best to replace the drive technology with a tooth belt driven by servo, as the belt gives us nice possibility in terms of maximum speed, but due to the design, it requires a large motor and its maximum power is limited. Or we can use ball screw for smaller strokes. It will also give us better precision. Still, we have to remember that the larger the screw pitch is, the greater the maximum possible speed. Maximum permissible speed and acceleration value of screw also have its own limits. Another possibility are rack and pinion systems, which have similar speed characteristics to belts, but with much higher forces and achievable precision bigger than even screws. But you probably wonder why we are proposing to replace pneumatic with other drives.
So, because if you replace a two-position pneumatic actuator with a servo with appropriate mechanics, as Błażej mentioned, we can take advantage of more advanced control and accelerate the machine cycle not only by achieving higher maximum speed, but also thanks to the possibility of shaping trajectories, optimizing motion paths, and the option of simultaneous operation of the drives in the collision space. In most cases, we are able to convert pneumatic system to electrical ones very easily, thanks to the electric actuators produced in the size of the pneumatics ones. Yeah, so there is a size standard. Anyway, we have electric actuators in our portfolio. So if someone is already interested in it, we invite you to contact us. In the package, we'll calculate the difference on total cost, not only of purchase, but also of use. Because pneumatics, paradoxically, is an incredibly expensive medium, which is rarely talked about.
Finally, the thing you need to pay attention to is the mechanical part, because we may face the situation that we are limited not by the servo, but by the capabilities of the mechanical system.
Yes.
In very high speed application, often the guides are the bottleneck, because even though we don't make long runs and speed, it's not a problem. We are limited by acceleration.
Yes, you are right. But okay, Błażej, it's at the end, yes, the end of the end. If you wanted to speed up even more, you would like to build the fastest possible machine with linear movements, for example, what you can do?
I would choose linear motors.
Okay, linear motors.
If you would like to achieve even better acceleration and speed, while getting, of course, also better precision, you should consider a linear servo, which can achieve several times higher linear acceleration, even up to 20 G.
Wow. Yeah, this is worth considering in new solution, because updating older machines can be a hassle in this case. And it is worth mentioning that day by day, the prices of electric linear solution are becoming more affordable, and it makes more economic sense given the possibilities they unlock. I think, by the way, that if you have been listening carefully to us today, you already know what I mean about these possibilities. So, this is the end of this webinar.